Okay. All right.
Holy crap. Wait,
No, it's going to be fine. This is going to be great.
Yeah.
So 7.4 we're going to do after. Okay. There's a reason that I do the differential equations, and that's because you have to know, I want you to know use substitution before we do this. Okay? Good? Okay, I'll stay closer. Free. Okay, I know. Sometimes if I'm not close by. Okay, differential equation. What's that mean? Differential. Okay, so it's a derivative. Okay, dy dx. This is a differential equation. Okay, what we're going to do today is we're going to start with a derivative and we're going to work backwards. You're going to think, well, didn't we just do all that? We did. But we didn't call it solving a differential equation. So what I want you to do, we're going to find all equations, or all functions, y, that satisfy this. Prior to this, I just said, evaluate the integral. I never said, here's the derivative, find y. But it's going to look exactly like what we did previously. So the first thing I'm going to do, multiply the dx to the right side. So I have dy equals secant squared x plus 2x plus 5 dx. So again, dy and dx are called differentials. So we separate the differentials. In 7.4, what we're gonna have multiple variables, but in this case, we're only gonna have the same variable on one side of the equation. Okay. Now, the only way to get rid of a differential is to integrate it. Okay? Now, on the left side, it's just an integral and a dy. But think there is a 1 there. So what would we get? Well, it's dy. So it would be y plus c, technically. Okay?
Wait, is that a 1 or a 1?
That's a 1. That's a 1. Because it's whatever variable we have here. So it might be a d theta, it might be a dt. So whatever variable, right, we just get that variable at the end of the differential plus c. Okay, on the right side, antiderivative for secant squared, tangent x, 2x becomes 2x squared over 2, so x squared plus 5 x plus another c. Now these, I'm going to just put subscript because they're not we don't know what the value of c is. Well, I don't want you to mistakenly just get rid of the c because they're not necessarily the same, okay? But my answer has to just be a y. So I do y equals tangent x plus x squared plus 5x. If I subtract c1 from c2, we don't care what it is. We just get a plus c. Now, in the future, I don't want you to put a plus c on both sides. I just want you to put the plus c on one side and not bother with this. Yeah. So all functions y. So I want to end up with y equals a function. So this is my answer. Does that make sense? Why we just do the c at the end? Yeah. Okay. Okay, find the general solution. Okay, general solution, again, that means I want y equals some function, and we're always going to have a plus c unless we have more information, which we don't have. We don't have any limits or anything.
So
okay.
What's the difference between this one and the last one? Why they're different, like general solution to all?
So I just want you to get used to the different vocabulary.
Oh, it's the same thing.
It's the same thing. So sometimes I'll ask for find all functions y that satisfy that differential equation. Sometimes I'll say find the general solution. I just want you to know they mean the same thing. Okay? So you should just be used to the different terminology. Okay, so first thing we want to move that dx over, integrate. Again, what's going to happen on the left side? Just y. Antiderivative for secant tangent, secant, minus e to the x plus e. Okay, so, and we can also obviously check to see did we get the right answer by doing the derivative. And we're good. Okay. Do you see how this is essentially what we've already been doing? It's called something different. Okay, we're solving a differential equation. So I have dy equals 1 over x. I'm going to write this as x to the negative 2 dx. I had to give you, the reason x is greater than 0, I needed to make sure that the domain made sense in order for it to be a function. Okay, 1 over x becomes natural log of x. Do we need to do absolute value? No, because I already told you it's greater than 0. If you put the absolute value and you don't need it, you don't lose any points. Okay, so if you want to just always put the absolute value, you're not gonna lose points for that. Okay, here I get minus, that'll be x to the negative 1 over negative 1, so plus 1 over x plus c.
Wait, why is it 1 over x?
X to the negative 1 over negative 1, so flip it. Okay, here we have dy equals cosine t e to the sine t dt. Okay. All right. In order to solve this differential equation, we have to think u substitution. Okay, so I'm going to let you literally just took the quiz on it yesterday. So we're going to let u equal sine t. So d, we've forgotten that. It was that long ago.
It's because they're multiplied by each other? No.
Yeah.
Because it's like chain rule, right?
Okay. Well, because we can't just integrate this. You can't like distribute an integral. So it's e to the sine t. So I make u equal to sine t, so du is cosine t dt. So that becomes the integral of e to the u du. Okay? Question? So we get e to the u plus c, which means our final answer is e to the sine t plus c. Okay. These are general solutions because of the plus c. All right, we don't know the value of c. On the next page, we are going to find out the exact function. Okay? Okay, how are we going to do that? And yay. These are fun. These are nice and fun. We're literally doing, it just looks different and we call it something different. We call this solving an initial value problem or finding the exact solution or a particular solution to the differential equation. Okay? So that's why I put here, we can't find the unique solution. This is where we would have a plus c. Okay, in the general solution, right, we would need to know more information. So we have what's called an initial condition. Okay, and then we use that initial condition to find out what c is equal to. Okay, good. All right, so here we want to find the particular solution to dy dx equals e to the x minus 6x squared. But we have a point on the graph. Okay, so here it's going to start out exactly the same. as the previous page. So e to the x minus 6x squared dx. So first, we're going to find the general solution. Okay? So we integrate. And I know it seems like a silly extra step, but I need you to write that out because this could potentially be a problem on the FRQ section of the AP. They want you to show separating it out. Okay? So don't jump right to y equals. Show the separating the dx and the integral of both sides. I know it seems kind of tedious to write all that out sometimes. There's a reason. Okay. All right, on the right side, we get e to the x minus, okay, that's going to be 6x cubed over 3. So minus 2x cubed plus c. Okay, now we take our condition 1, 0, and at this point, we're going to plug in 1, 0 and solve for c. Okay, so
And then you just plug C back in.
yeah. So I have 0 equals e to the first minus 2 plus c. So what does c equal? 2 minus e? Yeah. Okay. And then the last step, rewrite y equals and substitute c back in. So I get y equals e to the x minus 2x cubed plus 2 minus e. Yeah. Oh, no, that doesn't matter. Yeah, that doesn't matter. Okay? All right. Okay, so again, this is like a very methodical step-by-step. Move the dx over. What are we doing over here? Do I need to change some seats? Maybe a little less annoying. Thank you.
I was saying, you saw that. You're on my side.
I don't have a side. I'm on the side of. Don't be annoying. Don't be annoying.
Can you sign one seat to that corner?
All right, let me think about it.
No.
Okay.
You sign me that too.
All right, we integrate. On the left side, we have a equals, okay, these numbers are big, but I promise it works out nicely. 10x to the 9th becomes 10x to the 10th over 10. So x to the 10th plus x to the 5th minus x squared plus 4x plus c. Okay, now I am given a equals 6 when x equals 1. So we're going to substitute 6. Well, that's just going to be 1 plus 1 minus 1 plus 4 plus c. What do we get for c? So my final answer is a equals x to the 10th plus x to the 5th minus x squared. These are fun, right? They're kind of fun. Differential equations are my favorite part of calculus. They actually are. This and the next section. This is where it's at.
Slope field for the next lesson.
Okay, let's not get carried away. Shall we try the next one on our own? Yeah, try it on your own. Come on. Come on. Let me give you a couple minutes here. No, there's no u substitution here. What's the antiderivative for secant squared? Tangent. Yes. Yeah? Well, so this will be 3. Yeah. So that'll. Did you get it? Wait, no. What's the thing? Yeah, but your exponent doesn't change.
Okay, with the minus x to the 3 halves.
Did we get it?
Okay, I added the x to the 3 halves now.
Oh, okay.
In this case, if you look at mine,
Yeah. Yeah, you should get, because it's x to the 3 halves over 3 halves, so it cancels out the coefficient, but you still have an x to the 3 halves here. Plug in 0, we get c equals 7. Is that what you guys got?
I got that. Let's go.
Okay. Equations, I actually don't love slope fields, but they're necessary. You have to know how to do them, okay? What we are going to do, so when we think of derivative, we think of slope. Okay, slope. So basically what we want to do is take a set of points and we want to draw small little segments that show a slope at each ordered pair. Okay, so for example, if I take the ordered pair 1, 1, so if I do dy dx at 1, 1 for the differential equation x over y, what do we get? We get 1. Okay. Now, over here at 1, 1, we're going to make a segment that looks like a slope of 1. Okay? And we don't want to make it too long because we don't want all the segments to cross over each other, but we want to make sure it's long enough that we can see it clearly. So I'm going to just draw something. Again, how can we check to see if it's approximately a slope of 1? If I look at, okay, if I went over and up that same amount, that would be a slope of 1. Okay? Yes. So now, if I go, let's say to the point just above it, and I do dy dx at the point 1, 2, well, that will give me a slope of a half. So I want to make sure this is not going to be as steep, right? It's going to be more slanted. So it's going to go kind of up 1 over 2. So kind of imagine what that might look like. Doesn't have to be perfect. Sometimes students are worried they're going to get marked off.
Like that's the point of it. You draw it.
You draw it. Okay. All right. So we're just, now you don't have to write all of this work out. Okay. This is really just mental math. But what I want to make sure, what happens when the y values are 0? Okay, so it's undefined. So when y equals 0, dy dx is undefined, and we leave blank. Okay, we do not put vertical lines here, here, and here. So at these three ordered pairs, I'm just not going to draw anything.
Why? But it's 0. Oh, wait,
No, because the y is in the denominator. Now, when the x is 0, so when x equals 0, dy dx is equal to 0.
Wait,
so,
isn't it the other way around? When y is 0.
Well, y is in the denominator for
wait,
this.
well,
That's
I
why.
was thinking,
No, I know what you mean, but because dx is on the bottom, but we're looking at the actual differential equation, x over y. So that means at 2, 0, 2, 0, 1, 0, not 0, 0, I'm going to leave that one blank. And at 0, negative 1, we're going to put horizontal. So here, here, here. Yes, Betty. No, we don't. This is all just for your notes. If I were doing this, I wouldn't show any work. I would just fill in the graph. Okay, let's do some of these others. Let's say 1, negative 1. What's the slope going to be? Negative 1. So I just want to make like a kind of a symmetrical.
Do we have to do this right? Do we have to do this for every single dot?
You have to do every single dot that's given, unless it's undefined. Okay? So that's why all the ones along here we're just going to leave blank. Okay, negative 1, negative 1. It's going to have a slope of 1.
So if you just
Olivia,
if you just do one
don't
half,
ask me that question.
just do half and just symmetrical. I listen to this.
Okay. Okay. Guys, please. Negative 1, 2 is going to be negative 1/2. Okay. That's why I said, remember what I said right before we started this? And I said differential equations are one of my favorite. Slope fields, not one of my favorite, but you need to know it for the AP exam. So we are just going to do it. Okay. Why is my... What's going on? Okay. Don't know what's going on with my draw board. This is x plus y. So we're just going to add all the coordinates together. So it doesn't matter where we start. We can start over here at 1, 0. It's going to be 1. At 1, 1, it's going to be 2. So we're going to make it steeper. And at 1, 2, it's going to be 3. So you just want to make sure progressively it gets steeper and steeper. It doesn't have to be perfect. They just want to see on the AP exam that it's... Because we're adding. This is now x plus y. If I added negative 1 plus 1, that's going to be 0. Got it? Okay. 0, 2, it's going to have a slope of 2. 1. 0, right? 0, 0 is going to be 0. And negative 1. Okay. Negative 1, 2 is going to be 1.
I did on the wrong one.
Negative 1, 1 is going to be 0. Negative 1, 0 is going to be negative 1. And negative 1 is going to be negative 2. So we're going to make that steeper. Okay. Okay. Last one. Okay, this one is kind of nice because we only need to plug in values for y. Now, since y is in the denominator, all the ones on the x-axis we're going to just leave blank, right? What's going to happen when y equals 1? All the slopes are negative 1. So what's nice about when it's just in terms of y, all the rows are going to be the same. If it was just in terms of x, all the columns. Negative 2 here.
For negative 1.
Uh-huh.
Oh.
So we don't have to plug in x. We're just plugging in the y value. So here it'll be negative 2. So these should all look...
How is that negative?
Oh, sorry, 1/2. You're right. 1/2.
Oh, wait.
So a little less steep. We said we're going to leave this blank. And what happens when y equals -1? 1. So we get 1, 1, 1.
Oh.